heating time constant and cooling time constant. When a drive is loaded, heat will be produced due to losses. That losses are copper, iron, and friction losses, and its temperature rises. The temperature rises beyond ambient value, heat produced flows out to the surroundings medium. As motor temperature rises, the heat outflows increases and the equilibrium ultimately sits in the heat generator becomes equal to heat dissipated into the surroundings medium. Motor temperature then reaches a steady state value. When operating for a specific application, the motor rating should be carefully chosen to ensure that the installation temperature never exceeds the prescribed limit. Otherwise, either it will lead to its immediate thermal breakdown causing short circuit and damage to windings, or it will lead to deterioration of its quality resulting into thermal breakdown. Insulation temperature limits are 90 degrees Celsius, 105 degrees Celsius, 120 degrees Celsius, 130 degrees Celsius, 155, 180 degrees Celsius, and above 180 degrees Celsius. That's temperature rise under the heating time constant. Come, let's go with heating and cooling curve. And this graphical representation shows time and temperature curve. It has maximum heating curve, that is maximum temperature rise while through the electrical drive operation, and that temperature reduced by cooling method where we had been applied across that operation in order to the letter representation PQ or STUV. So at the time of Q, gas start to condense, it becomes to little bit cool, then across R point it condensation is complete, gas condensation is complete. So the cooling, this is one kind of cooling method to apply opponent of temperature raised where we find out the ambient temperature. Next, liquids start to breeze the end of S. The curve T mentioned freezing would be completed. Next, temperature stay room temperature because the temperature completely slowed down from the high being level. So let us consider heating and cooling curves in the form of mathematical. An accurate prediction of heat flows and temperature rise inside an electric motor is very difficult to complex geometric shapes and the use of heterogeneous materials. Since the conductivities of various materials do not differ by a large amount, a simple thermal model of the machine can be obtained by assuming machine to be a homogeneous body. Although inaccurate, such a model is good enough for drive engineer whose job is only to select the motor rating for a given application, ensuring that temperatures in various parts of motor body do not exceed the safe limits. According that condition, the motor had been given some more heat generation, that heat total heat generated in the body equal to heat dissipated in surroundings medium plus heat stored in body or heat absorbed. So instead of heat generated in the body, we took W dt. W is work done by particular motor, into dt is variations of time the work having through, equal to heat dissipated to surroundings medium A lambda theta dt plus heat stored in body gs theta d theta. The equation can have to equilibrium under the mathematical condition operation. So we look at the on screen of explanation. So W dt minus A lambda theta dt, the A lambda theta dt comes from the right hand side of where we given in previous equation. So we come out the common dt. So W minus A lambda theta into dt gs d theta. Now we have the separate arrangement for the purpose to sort out this heat dissipation to cool absorption. So dt divided by gs A lambda equal to d theta divided by W A lambda minus theta. This will be second equation. Now we have to form those two equations according to our conveniency. Generated heat equal to heat dissipated. Already I told you generated heat is WDT, heat dissipation is A lambda Tm dt. Now we strike out both the common letter dt. We come out W equal to A lambda theta m. That theta m equal to W by A lambda respect of the above explanation. Now the theta m value is replaced in second equation. dt divided by gs A lambda equal to d theta divided by theta m minus theta. We make this equation into integrating both side of. So A lambda gst equal to minus ln theta m minus theta plus constant, integrating constant k. This equation is fifth equation. Now we have to replace t equal to 0, which mean the initial temperature is 0. Theta equal to theta 0, which mean there is no angle of temperature in beginning of electrical drive operation. So theta equal to minus ln theta m minus theta 0, where the t is coming, we have to replace the t value and theta 0 for theta. Finally we get theta equal to theta m minus theta m minus theta 0 per e per exponential minus A lambda by gs into t. So we took a gs A lambda equal to tau, thermal heating time constant. Already I told the steady state temperature theta m always having 63.2%. Now we just apply the heat, replacement of heat is cooling method. Come, let's go with cooling method. This is formulation of cooling method. It has heat generated in the body plus heat stored in body equal to heat dissipated to surroundings medium. Already I told in heating curve explanation, the heat generated in the body is W dt, heat stored in body is gs d theta, heat dissipated to surroundings medium is A lambda dash theta into dt. And this all derivation comes from heating curve derivation under the concept of homogeneous body in motor. So representation of this concept, we had been reduced the ambient temperature where the motor produced the temperature. So finally the cooling method achieved by this explanation, mathematical explanation across the ambient temperature of motor. This is comparison of AC and DC drives already I told you all. Thank you.